My talk's on scientific benchmarking, measuring and mismeasuring performance. I'm just Dominic Tarr on the internet. I do mad science and open source stuff, and thanks to Nearform for sponsoring me a bit while I do crazy stuff. So, an observation. Sometimes benchmarking is like science, but other times it's more like sport. Sport benchmarking. Contestants are raced over an arbitrary course, and then the winner is awarded a prize. The object of the benchmark is just to pick a winner. Whereas scientific benchmarking is when software performance is measured in order to understand or verify the program. The object of the benchmark is to learn about the program or about the problem. So sport benchmarking just asks which, but not why. Sometimes arbitrary and narrow, and most micro benchmarks you see are really probably more sport than science. For example, I got a pull request recently to change from square bracket .slice.call arguments to cache the array.prototype slice and slice.call arguments. And this was an actual pull request I got, and I was like, no way. Like, that will make no difference in practice. By the time that's in an actual program, all of the other things you're doing will totally overshadow the thing. Unless this is on a very hot path, make no difference. And if it was on a hot path, you can make it way faster than this anyway, because slice there are faster ways to do it than slice anyway. So they link to, not actually this, I realized just recently, this is actually completely the wrong slide. But it basically looks like this. With JSConf, you get a bunch of like single data points for different browsers. You can decide what browser is the fastest, but it doesn't really teach you anything about how the programs really behave. Like, you can't see any of the variables. Yeah, show me a program where this is actually measurable. Here's another one that's a bit older. So back when Node, so there's this other thing, Vertex, which is like basically the same idea as Node, but on the JVM. And this guy published this micro benchmark where he benchmarked a server with just a 200 response. So hello world, and there's one that's served to file, and it's like, oh, Node is really slow. But the other one where it's served to file, commenters soon pointed out that Vertex internally uses mmap, which loads a file directly into memory and then reads from memory. So it was essentially caching the file in memory, and when you did the same thing with Node, you got pretty much the same thing. So really, this became just an argument about who was right, not what was right. So these things like this, I think, should totally be called out and be like, that's not rigorous, that's just marketing. So scientific benchmark is about learning and not about winning. You need to have a controlled, repeatable experiment. An emphasis on experimental, not theoretical. If you ever did computer science at university, then hopefully you learnt about things like big O notation and different orders of complexity and stuff like this. But in practice, that stuff doesn't really doesn't apply as well as actually just measuring the thing. And I found that when you do measure things, you'll be surprised. So the thing that I've been benchmarking the most recently is a module called Crypto Browserify. So Crypto Browserify is a partial implementation of Node's crypto module, but works in the browser with Browserify, so you have the same API for a subset of the features that people have needed and made pull requests for so far. So it started because I just needed SHA-1, and more recently other people have been helping out, and I decided with some recent events that it was time to take this a little bit more seriously and to measure how well it performed and how well other crypto libraries performed. And so I did some tests. So I got a whole bunch of all the crypto libraries I could find, and I just experimented how long does it take to hash a file with varying file sizes from very small to very large. Well, as is feasible, large, like 10 megabytes is large for most of these. This is just a graph of the y-axis is the size of the file, so 0 to 10 megabytes, and the y-axis is the milliseconds it took. So you see some of the, doesn't quite fit. So some of the libraries are not very good. Some of them are quite good. They're all mostly linear, which is a good sign. Means nothing horrible is wrong. And my implementation was up here before, and I managed to crib a few improvements off Forge, and I got it to quite good. And then later, after I did this, I discovered that there were some other modules implemented that did even faster than the one I wrote. So Git SHA-1 and Russia were way faster, not very clear, which you can't see quite clearly on this graph, but when you do bytes hashed per milliseconds, you can see quite clearly which one is the fastest. This red one is the one I implemented. This blue one, turquoise one here, is from the Git.js project by Tim Caswell, and this is called Russia, and that is by far the fastest, really fast, for JavaScript. Incidentally, to put this in perspective, I've compared this to, so doing a hash in JavaScript is about the same as using OpenSSL on a Raspberry Pi, compared to like a MacBook here. So that is important. So clearly some of these, an interesting thing here is that the most well-known crypto libraries are actually these ones. Crypto.js, Stanford JavaScript crypto library are actually, for this test, for the hashes at least, are the slowest. There's much, much better libraries out than there. It just shows how much you can improve JavaScript by paying careful attention to what you're doing, and probably what you've implemented by default probably isn't very fast. These two are interesting because they have this non-linear step where it goes from relatively slow, and when it gets to about 2 megabytes of size, they become dramatically more efficient. Now, these both use node buffers, which could be why. More investigation is required. So maybe these, maybe if we try some different variables, we can find different results. So maybe if the hashes are we just hash small objects, or we do iterative hashes, maybe the other libraries have been optimized for those. So I do another experiment with password-based key derivation function with increasing iterations and see what that looks like. And I got this. Now this was very surprising because there's something, this shape is very bad. There's something horribly wrong about Crypto.js. It seems to have sort of exponential, totally non-linear performance. That would not have been obvious if I hadn't made a graph of it. You'll just see that it's subjectively slow, but there's probably something very wrong that could probably be fixed quite easily once you've figured out what it is. So to look at that as iteration per millisecond. Now, this is something that's actually been very optimized in SJCL, and I haven't been able to figure out what it does so well just yet. My implementation is in the middle, about the same as Forge, which was a fairly good one. So there's future work will be things like benchmarking the memory characteristics. So one thing, Russia had the fastest performance, but it had to buffer the entire file and then hash it all in one go. And usually when you hash one, if you're dealing with a single file at a time, it's fastest to load the whole thing and then process it. But if you have to load hundreds or thousands of files, or you have a web server with many, many connections, then you'll use up a lot of memory, and maybe just waiting and doing all the CPU in a chunk at the end will be slow as well. Whereas if you're streaming, you can do the CPU processing in the gaps between, while you're waiting for more chunks to arrive, and your computer is basically sitting idle. So overall, it'll be faster if you're doing more than one thing and waiting around for things to happen. But that needs to be experimented with to see where it changes from being slow to fast. When faster to buffer to faster to stream, or viable, or no longer viable to buffer. And this is another thing that I'm working on too, is benchmarks for LevelDB. So LevelDB is a Google open source embedded database library. There's tons of modules. One thing we might want to test is, have we done something stupid that's ruined the performance? And there's a whole bunch of different forks of LevelDB. It's used as the default backend in React now, and there's a HyperDex LevelDB variant, and so we want to test these and see, are we using the best one? But a database is unlike these like hashing algorithms, is that there's a lot of variables we can be testing. So what I present here is only really just scratching the surface. So this graph just shows the time it takes to write 100,000 fairly small records. All of these databases tested are approximately linear. Lower means it took less time, so that's good. This one here is the Basho and Google LevelDBs. This one here is HyperDex. There might be something wrong with this because that's meant to be faster. And this one, the red one, is actually a subset of LevelDB that I implemented in pure JavaScript. So that is only Node, and it's actually doing pretty well. Like, it's only like slightly slower than the Google LevelDB, which is written in C and that sort of stuff. Like, how is that possible? So basically, I think it's possible because all you're doing is really appending to a file. And basically, the less that you do, well, you're doing two things. You're appending to a file that saves the data, and you're sticking things into an in-memory table, because the first part of LevelDB is just a memory table. And you can actually see these little vertical steps in various places, which is subjectively perceivable when you're watching the benchmark output. And those are unmistakably garbage collector pauses. So in 100K, a database of 100K records, the database turns out to be like 300 megabytes in LevelDB thing. So you've basically built one JavaScript object with 300 megabytes worth of data in it. And when you have that kind of size, scale, heap in V8, you'll get noticeable pauses. But it's still doing impressively well for something that's a database that's implemented a dynamic language. Now, this will have probably loads of other, it looks very favorable in this situation. There'll probably be lots of other things where it is not. But I only did this yesterday, so I'll have to do more tests later. Here's another experiment where it's like, what happens if how much difference does it make if you write to the database in parallel? So if you have one put and then you wait for it to return and then go again, how fast can you write a certain amount of data? Or if you do a whole bunch in parallel, how much difference does that make? And so each of these data points, I wrote 1,000 records, small records to the database. And then for the next data point, I deleted the old database and started completely again so that it couldn't interfere. So each run was independent. Now, the red and the blue are the Google LevelDB and the Basho LevelDB, and the red one is actually the pure Node.js JSON log DB. So that, quite surprisingly, actually gets better the more parallel you make it, and it gets competitive at about 10 and looks like significantly better at about 15. That was quite surprising, but more tests, more experimentation. I didn't expect it would be that viable at all. It's basically, it's converting. You give it some data, it JSONs it, and then just stores it in a line-delimited file. But it looks like maybe that's really fast, and maybe you can even build a viable database that way. So there's a lot of future work. It's really easy to test random keys, but most databases don't look like that. There's like all languages have like properties about them where you have, you know, some very frequent words, some infrequent words. All services have like some resources that are very popular, some resources that are unpopular. This means that sort of caching is possible and things like this. So if you want to test something, you want to build a better model of, you want it to use to educate your model and to get performance in real world situation. You'd have a model of what the real world is that you can test your performance against. Does the read-write performance vary as the key value size increases? Is it linear, or does it hit a non-linear point? Usually you have massively more reads than writes. So do different mixtures of reads affect writes affect read performance? How does performance vary if we do distributions of data? Like if the data inside happens to be appends or prepends, does the performance change? Appends and prepends are very interesting because that's one case where you could use a more specialized database, aka a file that you append to, and then you could have a database that only appends, and it would be could possibly be faster than a database that is more general purpose, like LevelDB. Of course, CPU is not the only resource, it's just the easiest one to test. Bandwidth, latency, you should track the percentiles, not the averages, so you want to know how much variation there is in latency, because that's what makes it unpleasant to use. How much memory you use for abuse, like do you have like garbage collector pauses to the leak memory? That's somewhat harder to test than CPU or bandwidth. And is there some point? Like the nonlinear effects always like show that you've discovered something. There's something that's happening whenever you get like a kink in the graph. So you want to look for those. Like in theoretical computer science, they just like, oh, you just model it as a curve, but then you have this abstraction where you have like infinite memory, hard drive space, and that's just not realistic. So in practice, we'll always have nonlinear effects. When do they kick in? So basically, to do an experiment, you need to figure out what all the variables are and control all of them except for one, and then graph the results. That's more or less the simplest possible thing. Usually there are lots of variables, but science is challenging. That's the way it is. So this is a quote from Richard Feynman. The first principle is that you must not fool yourself. You're the easiest person to fool. After you have not fooled yourself, it's easy not to fool other scientists. And it's a kind of scientific integrity, a principle of scientific thought that corresponds to a kind of utter honesty. If you're doing an experiment, you should report everything that you might think might make it invalid. But that would be like, for sport benchmarking, that would be like telling everyone about your flaws and weaknesses, which would be bad strategy for sport, but the only strategy for science. Thank you.